So I want to welcome everyone and thank you for joining us today. We're excited to have you here in this session on dynamic beam lasers for e-mobility application. Mostly that's what we'll be presenting today. Our speaker today is Dr. Robert Bernhard, Application Lab and Branch Manager at Civan Lasers in Hanover, Germany. Robert holds a Master of Science in Mechanical and PhD from Laser Zentrum Hanover and have a lot of experience during the last years about about applications for the automotive sector industry with laser. Prior to joining Civan, Robert spent nearly 5 years in the Laser Zentrum Hanover, where he served as the head of additive manufacturing and metal group. There, he led researches in laser-based metal additive manufacturing and process development for industrial application. At Civan, he now leads the application lab and supports customers in implementing dynamic beam laser technology. He hosts many visitors, and I would like to invite you to visit us in Hanover and see for your own eyes our application lab and facilities over there. As the webinar progresses, please feel free to submit your question anytime using the Q&A box, which appears at the bottom of your Zoom screen. We'll address them during the dedicated Q&A session at the end of the presentation. So with that, I'll hand it over to Robert. Robert, the floor is yours. Take it from here.
Perfect. Thank you for the kind introduction, and I'm really happy we were chatting about this prior to the start of the webinar, that today I will present e-mobility applications. The dynamic beam laser is a great tool for many of these applications. I want to focus a little bit on the things we are currently working on, and we are currently working on at Civan in Germany, but this is just maybe is a start of it. And what we are really like to do is to also give you a feeling about what dynamic beam laser actually means. And you can see it here in a high-speed video. This is slowed down by almost 1,000 times. What you see here is the spiral. I think it's a very recognizable shape, welding aluminium. And to use this as a starting point, what you see here, and I think you can see it right here in the center of the melt pool, is this dynamic aspect of the beam shaping. So it's not a static spiral. We have something really steering inside the whirlpool or melt pool, and this is something where we build our applications on and have our success in laser processing, which means, and the idea is, we are pushing the boundaries of what's possible, meaning that we can now weld materials that are hard to weld or we're not able to weld as of now. And using dynamic beam lasers, I just want to give an overview and some insights into what we are currently welding, and keep it open for discussion at the end of what else you can think of to weld. Let's just do a very basic technology fundamental thing, because I think what you need to know about our lasers, if you buy one of our lasers, you get multiple lasers, and these do constructive and constructive interference, which means in the end, you're getting multiple laser fibers that do the interference patterns on the workpiece in the focus spot. And this means at first we have really precise control of the beam caustic, but also by using coherent beam combining and detuning some of these fibers, we are able to move this interference pattern around. And this is key in order to be able to do high-speed modulation of the laser and then also of the beam shaping. So we are talking about dynamic beam shaping inside the focal area of our laser. So this is nothing mechanical. It's purely electro-optic, and this means it's fast. Fast here, we are talking about megahertz of phase shifting, which results in also, above 1 megahertz frequencies where we can move around shapes. And we see that workpieces and metals, especially in welding, can really react to this different frequencies and the refresh rate of these shapes. Which means, if you think about it, when we go for a conventional scanner welding, the upper limit are somewhat of 2 kilohertz. And this is where we just start, and we would say this is something dynamic, where the process, the keyhole follows the material keyhole follows the laser beam. If we go higher in frequency, we go through a resonant regime, which is also really important for the process, because this is where we are able to get rid of impurities during the welding. This is something highly important to the welding in terms of frequencies. For aluminium and steel, these are usually 10 to almost 100 kilohertz, I would say. And beyond that scale, we get up to quasi-static beam shaping. And quasi-static beam shaping is more or less what you see here, integrated over some time, that you see this beam shape. And of course, we can do sequencing, but we'll talk about that later, that then result in moving intensity distributions. So something I like to point out in my talks is it's really important that we are using these interference patterns. And if you look at the lasing at one instant, you have an interference pattern. But we are so fast. We are again talking about up to 80 megahertz of controlling individual phases. This leads to megahertz speed of shape generation. Then results talking about, let's say, some time in a second, or even in nanoseconds, we can trace out all the dots that make up an interference pattern like this nice smiley here. So this is over time, but it's very important to know, I think, that the beam shaping itself is very dynamic, and we can control the dynamic aspect of it and tailor it to our process. And by doing this, of course, we have new degrees of freedom by starting with the shape itself. So we can design shapes, we can program them simply, but then we also have more parameters, like talking about the shape frequency, shape sequences, where we have different shapes one after another that can influence also flow situations in melt pools and so on. And finally, this also enables, by clever focus or by clever frequency shape shifting, also do some kind of focus steering, having an electro-optical Z-axis. These are the most important new degrees of freedom, and put them into action. You see on the right side, our shape generator it's as easy as this, generating new beam shapes, sending them to the laser, and start working with it. And I mean, sequences can consist of 28 shapes each. Here, as a starting point, I have a few combinations that are known for good parameters in terms of when we want to get deep penetration. We have something in our recipe book that works by having a confined, but then also some laser widening of the melt pool and so on. So this works for many things, and it's really that intuitive in terms of, I want to have a wider beam shape, but I still need some concentrated preheating, post-heating inside that laser beam. You can quickly start at getting different kinds of sequences click together, and you're good to go. And this also leads to our programmable beam shaping, also that we have this capability of, without rotating our head, we can rotate the beam shape. I think you may have saw it at the beginning on the intro video, but also here I think it's on the right side. It's more schematic and easier to understand that without turning the laser head, we can actually rotate a beam shape that here is 2 dots. You can also see this here on the high-speed camera where the 2 dots are tracking the rotation of the circle. So this circle is done by using a scanner, regular scanner welding, but then the beam shaping inside the melt pool, this is where our technology is key. And let's dive right into it. We've made some good progress with aluminum battery coolers in Hanover. Just to give you a feeling of what we're working with there, it's a really flexible setup where we have the laser head with the scanner up here. Then we have quite some remote welding. And down here, your jig can be, in this case, this is just a simple demonstrator jig for welding these cooler plates. So you can see me putting one in here and then welding them remotely at high speeds. So the key aspect here is, and I think I forgot to mention it, but welding these coolers, and these coolers in e-mobility are usually big parts, 2 meters by 1.5 meters or something, with a lot of weld seam length on there. And the challenge is to weld them leak tight, but also to weld them really, really fast. And welding them really fast is, of course, a challenge due to the material in terms of getting the energy where we need to have it, as well as getting it crack-free. And when we're talking about high-speed welding, my definition of high-speed welding here is 30 meters per minute, so 500 millimeters per second, and that's our target welding speed we wanted to achieve. And well, as a starting point, we wanted to go with just a single dot. That's to make it somewhat comparable. But to spoil it a little bit, the single dot is no way of getting this this welding done correctly. So what we developed is a dynamic ellipse that has 100 kilohertz of shape refresh frequency and consists of 25 individual points. You can see how this is made up here in our program on the bottom, and it's important that our welding is aligned like orthogonally to this line. So the leading edge kind of is on top, and this makes for especially wide weld seam. And of course, using the scanner rotates, like we saw with the 2 dots, it also rotates this ellipse electro-optically. So this means, like we were talking about, this is really, really fast. You can see the video speeding up. It's 100 kilohertz, so I can't show you, but what you would see, or what the workpiece here experiences, is 100 kilohertz shape refresh frequency. That means every single dot is only on for 400 nanoseconds, and this enables us to get the steering inside the material and open up the keyhole capillary, as well as getting the process on point in terms of still doing high speeds, but getting the solidification right and getting rid of cracks. What I mean by this, so by using a single dot, we have, of course, deeper penetration. This is something we understand. But at the same time, we get a lot of imperfections. And looking at the cross section here, it's at these high speeds, we are still experiencing some fume issues, but it's no cracks. It's without any inclusions. So we are really happy that we can achieve these high speeds by doing this laser welding. You can even see it here, I think better on other aluminium, where we can achieve also at a little lower feed rate, but getting very wide weld seams. So dynamic beam shaping here as well helps us to get the weld seam tailored to our needs. And well, talking about this cooler in specific, we are using this demonstrator here because it's a non-NDA one. We can openly talk about it. So it's a dynamic ellipse, 500 millimeters per second. The top plate is 1 millimeter thick. The bottom plate is 2 millimeters thick. And we are able to achieve with this design leak tightness. We specified as 2 bars, but I've seen the coolers bursting at 6 or 7. And then it's usually due to the design because we have like inflation of these size. So there's, of course, some challenges to overcome at these high speeds. And I would argue that we can even widen the process window to get rid of undercuts. But in general, it's really important for us to have the leak tightness, and this is what we are able to achieve with parameter set. I'm of the opinion that we can also do then outside do construction or structural welds as well, but the leak tightness here, the long welds we need, we are able to achieve on 500 millimeters per second. And finally, one thing we are currently working on is to substitute the argon. So these processes have been done with argon shield gas in order to reduce oxidation. But finally, getting rid of argon, which is just a consumable, is one of the next steps, while even increasing the yield rate, the process window, maybe making it even wider or working on the surface finish. But for us, this is definitely a breakthrough in achieving 500 millimeters per second, 30 meters per minute, consistent welding speed, leak tight on these aluminum plates. Something I also like to show a lot is the difference between or when you start to measure your laser process. There's pretty nice tech out there. In this case, we used a 4D sensor, but also the Precitech LWM works well. We've proven it, and the Plasmo process observer is also a very good option. What I find interesting, and I think what someone can see is that, again, talking single point versus our dynamic ellipse, we get a lot of cracks, or we get cracks during the welding, but also what we get is a lot of back scattering, which we attribute to the keyhole collapse that we can see during the welding. So the signal you see here is back reflection in different wavelengths from the process zone itself. And if we switch to our developed dynamic ellipse, it almost becomes good. So this is something manageable where in serious production we can specify a threshold and just see that this is a very stable and good process, I would argue. So to underline this for our Civan coolers demonstrator, we have this dynamic ellipse that has less penetration width or depth. The width is wider. And we get with this dynamic beam shape, following the path of the weld, get leak tight coolers at 500 millimeters per second. This is something we weren't able to achieve, and I think no one else was, to my knowledge at least, was able to achieve this high speed without cracking. In other typical Gaussian configurations. I mean, this is also a nice thing about the scanner where the process speed is not limited by any axis, and this is something we can do with our laser as well. Stepping back a little from aluminium, but in the scope of the e-mobility we are talking about, I think it's a must to mention copper. And you already see the first results here with copper welding in terms of bus bar applications, talking about the welding of hairpins. This is, I think, something where there's a lot of ideas using different wavelengths, blue and green. is a decent approach, but I think nothing beats the high quality of our welding in infrared, high power, perfect beam quality, and stable keyhole. And now by introducing dynamic sequencing, this means we can do fun things like melting the copper hairpin by placing 4 individual dots alongside, or even a line would be possible on each of these hairpins, and then switching to something more random. This means we have something steering and connecting them. So you get really this pearl being generated. So we see also in copper, I think this is something I published for the Lane conference just last year. Doing beam shaping allows you to get very good penetration, get rid of spatter, as well as making sure that the weld seam itself has the right dimensions. How we do that? For copper, we need high intensity to just get the process started. And this is something we can do very well by doing constructive interference in a single point. So this is an interference point. You see it's really small, condensed, around 85 micron in diameter. But then I switch every 200 microseconds to a different it's kind of an arrow shape, but with a stir bar at the end. That's the idea. So top again is leading edge, and by welding this way, the high speed also shows that we are keeping the keyhole open for longer. We are avoiding collapses, and by distributing the heat, we also get around overheating the material itself. So there's no spatter, no melt pool explosions happening. Well, and this finally leads to things like busbar welding, laser welding of around 5 millimeters material thickness without blowholes and spatters. So I think this is also a very interesting application where with our laser you can do copper welding and even advance and enhance on typical static ring core things, and you don't even need to bother with blue and green then. And building on the copper thing, now we were also talking about aluminum before, but this is something I think one can easily imagine how the steering and the beam shaping definitely also must have an influence on intermetallic mixing. And intermetallic mixing here we mean by, or we show it by using aluminum on copper. And by doing this and then changing the frequency, which means the frequency, this shape, in this case, it's a spiral that's drawn. When we change the frequency of the shape drawing, we see that there's an influence on how well materials get mixed. And I mean, copper and aluminum, they don't like each other, so you get a lot of brittle phases. But if you can steer it up and get it less concentrated, and I think this is something we can show here, it's possibly also an enabler for these intermetallic mixing and intermetallic weldings, at least. This would also be true, a different parameter set, but also be true for coated materials where you might want to get the aluminum silicon coated steel plates, and you want to dilute kind of the material into the base material, so you get rid of it. You don't need to vaporize it. So then there's a way of saving process steps at the same time. And building on this, and I think also a very, very nice application here and results we want to show is the welding of aluminum die cast. The idea is to replace processes like friction stir welding, but also to replace long process chains where you have to mill your part and make perfect adjustments, when you can just use a laser welding to do welding of raw, like from the casting ejected aluminum die cast parts. So not much machining. And what we see here is very nice cross sections here. Of course, there's some porosity, but it's highly reduced in what you would usually get with laser welding, which means here we are able to achieve less than 3% of porosity, while also keeping the inside of the part intact. So you can even weld this with having electronics inbuilt. And here we're talking about a thickness of 2 millimeters and more. I think the thickest material we welded were around 10 millimeters of aluminum die cast. And doing this with the laser with our dynamic beam shaping in terms of the spiral, dynamic spiral, we get the opportunity to remove the material, the porosity out of the welds. I mean, and then you can also start playing with the dynamic beam shaping frequencies, and but then is for die cast, I would argue it really depends also on the die cast quality, what you can achieve. So maybe 0% porosity is a stretch, but because the base material has some porosity, but at the same time, I think there are ways of melting and degassing these materials at the same time. And I think this is a good illustration where our high frequency beam steering elongates the melt pool, makes sure that the capillary stays open, and kind of also collects the porosity and the bubbles from the side that occur during welding, but also the ones that are already diluted into the material. And something very interesting to show, I think, is that there are sweet spots in terms of dynamic shape frequencies. And now it's more on the scientific side, but I really find this fascinating personally because you can kind of see a trend where we are here in the dynamic regime, and then we go to the quasi-static regime, and quasi-statically, this process doesn't work. We have a lot of porosity. There are problems with hydrogen exploding, kind of. But if you find this sweet spot in welding shape frequency, which you can easily do with our laser, doing some frequency sweeps, you get into a region where there is, let's say here in this example, 20 kilohertz. There's a very well behaved weld seam. Not much of porosity, or at least in spec porosity. This is here below 2%. Something we are really happy with welding aluminum die cast. It's fast, it's hassle-free, and you don't even need argon for these. So these are purely remote welding without any shield gas. And this is, I think, sums it up really well. Compared to friction steel welding, we are way faster. Our dynamic beam lasers, 9 meters per minute, if not even faster. And I think this is a very good application that we also in Hanover building our business, expanding in this direction, doing more and more of this laser welding. Finally, and I hope you're still interested, is on this topic of high-speed welding, is welding steel. And this is something, steel welding at 500 millimeters per second, which is pretty fast for 1 millimeter overlap. And the challenge you usually get by these high-speed welding is that you get that gets better, and you get bulging, where the molten material kind of bulges or adheres together, and you get these bubbles or these problematic zones here. And what we found here is that when you look at this video from left to right, we increased the shape frequency. The shape here was something that was something like an infinity wobble pattern, but doing this wobble pattern at frequencies of 30 to 100 kilohertz is way faster than any mechanical scanner can do. And you see that you start with a lot of spatter in the high speed, but then you finally end up at a sweet spot of 50 kilohertz where there's no bulging, almost no spatter, and then the bulging at higher frequencies then comes back. So this is something really interesting in terms of how the laser parameters can affect your process. And if you think about something that doesn't work for you yet, in terms of, this is something high speed you cannot weld, we get a lot of spatter and problems, then maybe even the dynamic beam shaping can target exactly this problem and start welding at speeds where otherwise, another laser couldn't be working. This all is usually also backed by simulation, where you see when you use the single point in this case or any other static beam shaping, you get a lot of cracking in the center. But when you start oscillating, you are able to stabilize the keyhole and even increase the size of the material. And I would argue in the end, most of this is a solidification problem in terms of thermal gradients. And this is definitely something we can adjust by changing the flow and also changing the energy input, how it goes into the weld seam. And suddenly your welded steel can become good when you start your way with dynamic beam shaping. This also goes for welding over gaps. This is something, but then usually you have to start with the filler wire. This is something work in progress. Usually we are able to get very deep penetration of butt welding. You can see it here, 15 millimeters of aluminum, 30 millimeters of stainless steel, up to 70 millimeters. Now we're talking 100 kilowatt laser power territory, but this is something where you can do these things in a single weld compared to manual labor, like doing weld after weld and inputting a lot of heat and time. This here, I think, is something where we can do welding even thicker structural steels, mild steels, which also, of course, play a role in automotive stiffness as well. Maybe also a fun thing, but this is quick welds using a scanner going over more complex 3D surfaces. But this is just a way to show that our laser can do electro-optic focus shift and doing motion on the fly, which the scanner and the access system we have is in preparation or is prepared for. We can also do that. And I think with this, I hope I gave some kind of overview of what we can do, especially for these e-mobility tasks. Maybe it caught you in maybe you have an idea also for your application. What I would like to emphasize on is that with our dynamic beam laser, we have the capability of control the thermal distribution in our weld seam. This is backed by high-speed cameras, cracks, and simulations. But at the same time, the molten flow is really, really important to manage for all kinds of materials. This is valid for copper. This is valid for aluminium. And doing this dynamic beam shaping finally results in stabilizing key and weld pool geometries. We can, as we've seen, tailor weld geometries in order to meet requirements, make them stronger, make them wider, as well as doing adjustments in solidification rate and going through the material, making sure that maybe even the material composition in the end metallographically can be adjusted, but this is something I would argue we can try and together then. And with this, well, I said it already. We are happy to host customers in Hanover. We are now a team of 4 people working there. We have a 14 kilowatt laser in our laser cell. You can see it kind of hidden behind this. And yeah, this invitation goes out to all of you. And now I'm excited to also answer questions.
Thank you very much, Robert. And now we switch to your questions. We have a few questions from our audience here. I'm using a spiral pattern of cast aluminum. How much penetration can be achieved with 2 kilowatt on 6 kilowatt laser? I'll just mention that we have multiple laser power that we can achieve from 6-7 kilowatts up to 100 kilowatts. What is the resultant porosity like? Do you still have the balance of porosity formation with penetration and weld speed?
So wow, three questions at the same time. So penetration wise, like ballpark numbers speaking, with 2 kilowatt laser power, you usually do at a 50 millimeters per second speed. I would argue that 2 to 3 millimeters penetration can be achieved. This, of course, then depends on the speed and the things. At 6 kilowatt, you can already weld 5 to 6 millimeters. That's, of course, a balance. And I think on the second questions, we are really good on the porosity. So there's, of course, some process development to be done, especially if your die cast material is difficult. Like there are different qualities and kind of the die cast materials. If the base porosity is less than 3%, I would argue that we can also achieve this less than 3%, usually depending on the parameters. We've seen perfect welds that are like less than 0.1% of porosity, but this is something we of course have to try out. And yes, so the porosity formation and weld speed, there are some ways of getting around this. Things like doing a double pass. I personally don't like to do double passes because it takes more time. Most of the time we get it right at the first time, but there are some things you cannot get around if your die casting is problematic in terms of diluted hydrogen that just explodes on you. Then at these positions we have to use our sensor technology. I just also we're talking about, but then you can actually redirect and go back again to this position and fix blowholes because you can clearly see this kind of imperfections. But yes, weld speed and penetration of course correlate. Porosity formation with our dynamic beam shaping is way reduced and something we can adapt from. So yeah, 150 millimeters per second, even 200 millimeters per second on a laser weld, I feel comfortable with aluminum die cast.
Thank you. So the next question, what would the argon be substituted with?
That's a good question.
Argon, yes.
Yeah, so this is a good point. Ideally with nothing, because argon is consumable after all. So what we see is that welding our coolers with argon tends to have a nicer surface finish. But mechanically, it's better to have a stronger airflow cross-jet over it to get rid of fumes, since this aluminium and especially the magnesium creates a lot of fumes during welding. And this is the balance. And ideally, we don't have any argon, or we're going to use this compressed air as a cross-jet and try to get rid of that. So substituting it with plain air, I would say.
Okay. And for the next question, Jules asks, what is the distance between the two dots at focus? And what is the maximum distance that you can settle?
So this is depending on your optical setup. The setup we have in Hanover is so that we have the distance between two dots would be 520 microns. So this is half a millimeter in size, but this is due to the setup we have in Hanover. We can also change the standoff distance and do some optics in there, and the current maximum we are working with is about 2.7 millimeters, so 2,700 micrometers, dot to dot distance. So it's like, to put this in perspective, it's of course small in terms of what you want to have, but the key aspect is that still our focal diameter is around 85 microns at these stages. So this means the maximum intensity we can do is like on this 85 microns single spot size, but then move them around at megahertz speed in this 500 micron, or let's say the 2.7 millimeter area. So it depends on the optical setup, and of course it depends on the application, but I feel the general sweet spot, especially for welding, where you still have the opportunity to have enough energy at the center and influence the melt pool behavior. That's something you do with this 500 micron working area, so to speak.
Thank you. And for the next question that we had, not the last, did you try the laser weld with dynamic ellipse for 6061 to 6061 aluminum? I can say that we tried. Yeah.
Yes, we definitely tried.
Yeah.
The nice thing is that the application lab in Germany that more or less just opened. So we were focusing on this aluminum 5754, but going higher in the aluminum area or numbering, we get the problems of hot cracking. But this hot cracking and the cracks appearing is something to be solved by also the thermal management and the melt pool. And I think, Roy, correct me if I'm wrong, but there were very promising and good results. I think even some qualified results doing this in an application lab in our headquarters.
Yes, it wasn't just dynamic ellipse. It was different beam shapes that we tried. You can, of course, change the beam shapes. And when we do a process development, we use different beam shapes. In this case, it was you ask for ellipse, but you can try many other beam shapes and finally define the right one for the 6061 aluminum. That's what the next question is. Is the less than 3% on the cast a volume ratio? Yeah, probably we have. Yeah.
Yeah, so the images we showed, and there were like many cross sections, but we also did CT scans, which unfortunately we can't show due to NDA stuff. But the volume ratio is less than 3%. I think this is something we can just like, this is something we can almost promise that we will be able to achieve this on good materials. But then it again really depends on the materials. But ideally, of course, 3% by volume.
Okay. Next question, how much physical space can you get with the output? Can you replicate a dual beam weld where the first scan is removing the plating and the second scan is performing the weld? Seems possible, but might need 300 micron or more of separation for gas to exhaust.
And I think he adds to it that this is for plated steel. And yes,
Mhm.
you're right. So doing something like this, removing or having some kind of separation, 500 microns here can be fine. I would argue that maybe then the optical setup should be a little bigger, or like that we can achieve that. And then it's actually a question of having beam shapes alternating quickly enough in terms of one gets the job done of welding and the other one gets the job done of removing the plating before. So this is something research institutes tried with our laser, and I think they made good results with ablating and then welding. Yes, so this definitely is something we are happy to try, and then it, I think, depends on on the material thickness. And I mean, if the melt pool is bigger than the stuff you want to ablate, then it's of course problematic. But in general, yes.
The next one is from Emmanuel. Thank you for your kind words and for your being here with us. Wish you a lot of success in your research now for powder assisted laser beam welding. And we too hope that you will be able to use our laser in your research. For the next question, with 2 millimeters, what will be the setup?
With 2 millimeters of well, depends on from what material. If we go for like for 2 millimeters, I would argue it's best to go for a scanner setup because this gives you a lot of flexibility and high speeds. I think the point where we go to XY motion systems, that's something where we get in the territory of materials thicker than 10 millimeters, or maybe at copper, maybe at 5 millimeters, because then you need a higher power, and there's only so much power we can push through a scanner. And yeah, so Roy, you mentioned it a little. We have our power ranges, the systems, how it is right now, 7, 14 kilowatts. These two can go through a scanner. Anything beyond that, talking about 28 kilowatts, 42 kilowatts even, or the 100 kilowatts, then there's unfortunately no scanner capable of transporting that much energy. And then you definitely want to go for deeper penetration. Compliment from before, thinking about collaboration also with universities. As of today, we are having in our lab a university trying out additive manufacturing. This is something with our laser that also works very well. You have this dynamic beam shaping, and I can only invite people to do even preliminary testing before in research you write a proposal. This is something we can do on a day basis. Just have to clarify the details, and then since we have this flexible setup, I think it's very easy for us to do in this application lab that we have to do this demo, but as well as do some initial proof of concept of things. Then, of course, if that develops further, then and we can build a business case around it, that's even better. And I think this is our main goal, that we in Germany now have this central hub for also European people to come and visit us. We are here for doing laser process development, but mainly doing proof of concepts, showing the technology and making it accessible. in terms of seeing it, but also servicing. So we build up our team that also includes maintenance technicians. If you buy a laser now in Europe, there's a good likelihood that one of our team will also help in the installation of that.
Okay, so ladies and gentlemen, thank you very much for your time. It was a pleasure to host you. And for further information, you can address either of us or you can just directly with Robert. And we'll keep in touch, of course, with you all. Thank you very much.
Yeah, thanks for the opportunity. I think we have all the details also on our website if you want to find me directly or anyone in the team. Yeah. Thank you, Roy, for hosting me. Thank you all for coming.